We're here to prove one property of similar triangles that is described by the statement corresponding edges of similar triangles are proportional. We have two triangles that are clearly of different size, but they have the same three angles written in capital letters, and as you hopefully know, any two triangles that have the same three angles are called similar triangles. And just as a reminder, what we mean by corresponding edges of similar triangles is two edges that sit between the same two angles on each triangle are corresponding. So for example, the base edge of both triangles sit between the angles B and C, so these two edges are corresponding. I'll label the edges of the smaller triangle with small case letters. We'll label the larger triangle in a similar manner, using the same letters to show which edges correspond to each other, but adding a symbol to the edge labels of the larger triangle to show that corresponding edges are of different lengths. We call the edge lengths of the larger triangle A hat, B hat, and C hat. Now what we mean when we say that corresponding edges are proportional is if, for example, I take the edge A and I multiply A by some specific value, the result will be the length of the corresponding edge in the other triangle, A hat. Let's call the value that we multiplied A by W, so that A multiplied by W equals A hat. Now if we multiply edge lengths B and C by W, the result will be their corresponding edges. So the edge B multiplied by W will give the edge B hat, and the edge C multiplied by W will give the edge C hat. Multiplying each edge by the same value will result in the lengths of the corresponding edges. And that's what we mean when we say that corresponding edges of similar triangles are proportional. Now, the way these equations are set up may not look very familiar to you, but there's another way of expressing this by dividing both sides of each equation by the edge length that was originally multiplied by W. So if we divide both sides of the first equation by A, we get the result that A hat divided by A equals W. And if we divide both sides of the second equation by B, we get that B hat over B equals W. And repeating the same idea on the last equation, we divide both sides of the equation by C. We get a similar result where C hat divided by C equals W, which means that the right side of each of these equations is equal to the same thing. A hat divided by A, B hat divided by B, and C hat divided by C equals W. And so that means that A hat over A equals B hat over B equals C hat over C. And so we can formulate that into one equation with three parts. And this is how it's normally written. And some of you may recognize this. And the purpose of this video is to prove that this equation is correct for similar triangles. And we're going to do that using the sine rule for triangles. So we keep the proportional equation to one side. And now we can proceed by showing the sine rule for each triangle. We'll begin with the smaller triangle. And just a reminder, we know that in the sine rule, for each edge, the edge length divided by sine of the opposite angle gives the same result. So the edge A divided by the sine of the angle A, which is opposite, gives the same result as the edge B divided by the sine of angle B, which is opposite, etc. So A over sine A equals B over sine B equals C over sine C. And now let's look at the sine rule for the larger triangle. The only difference will be that the edge lengths, which are different from the original lengths, will be written as A hat, B hat, and C hat. And so we have that A hat over sine A equals B hat over sine B equals C hat over sine C. And now what I'm going to do is, taking each ratio in a proportional equation, for example A over A, I'm going to express that ratio in terms of the sine rule for both triangles by manipulating the sine rule equations to find A hat and A, and rewriting the ratio. Now since we have the equation representing the proportions and the sine rule for both triangles, and since we're only calculating values, let's hide the two triangles, and that gives us space to do some calculations. Now to get the sine rule equivalence of A hat and A, I'm going to multiply all parts of both equations by sine of A. And as you can see in the first part of each equation, sine A cancels. And that gives us that A equals B times sine of A over sine B, and C times sine of A over sine C, and A hat equals B hat times sine of A over sine B, and also equals C hat times sine of A over sine C. And now we're in a position to write the ratio A hat over A, and that should give us a sine rule equivalent. Now taking just the second part of each equation, to get a hat divided by a, we can do a hat, which is b hat times sine of a over sine of b. But to divide by a, given this is a fraction, we can multiply it by the reciprocal, so that's times sine of b over b times sine of a. Now we can see that sine of b's cancel and sine of a's also cancel, leaving us that a hat over a equals b hat over b. And something similar happens if we focus on the last parts of each equation. We want a hat over a again, and this time that's going to equal, well, a hat equals c hat times sine of a divided by sine of c. And again, if we want to divide by a, we can multiply by the reciprocal, so we would multiply by sine of c over c times sine of a. The sines of a cancel and the sines of c cancel, leaving us c hat over c, which means that a hat over a equals c hat over c and b hat over b. So a hat over a is equal to both of these. We have proved that a hat over a equals b hat over b equals c hat over c, and so corresponding edges of similar triangles are proportional, and that's the proof complete. In the next video, I'm going to be using this property of similar triangles to show the proof to an interesting problem, so stay tuned for that video. Well, that's it for now. Thank you for watching.